So welcome. You can see I'm operating on 3 devices. Okay, my clock rings and we start. Yes, good evening, good evening. Okay, so let us start. As you can see, as I mentioned, I'm operating on 3 computers, right? So, okay, let's start. So the first thing is, which you would also have seen in your README first file, all right, the one which is in your Luminous. So clearly README first, right? So certain things, let's be very, very clear. So you've already seen, right? You are here, so that's very clear, right? The classes are online via Zoom, via our Luminous. Of course, you go to the conferencing tab. So the fact that you are here means that's clear to you lah. Okay, then okay, the question does come up, but university has told us to state very clearly. All right, so I state clearly one more time. University has said to final exam will be conducted in person, face to face. Okay, in some classroom on campus. So final exam will be in person, face to face. Okay, no two ways about it. So that means that students taking the module have to be physically present, right? On campus. Okay, module lecturers. There are 2 of us, myself and Prof. Ho. I will take the first part, right? You've seen from the lecture notes. Then my colleague Prof. Ho, he will do the second part lah. Okay, some basic information about the module. I just let you read. Okay, probably, okay, even module syllabus. All right, I'm not going to waste all the time to talk about all these things, because when we do it, it will be very, very evident and very, very obvious to you. Okay, so module syllabus, I also just let you go and read. Okay, at this point, well, it would be very, very clear, right? Very, very clear that what is very, very important in all your minds is how would the module be graded? Okay, some things which I'll say here will be very familiar to some of the students here already, because they have previously taken modules from me, right? I'm just checking my third screen to see whether they are already here. Yenan, welcome. Yenan took a module from me last semester. So he knows how I'm going to talk about. Okay. Then the other student has taken, never mind. Okay, so obviously you'll be interested in how the marks are allocated for the module lah. So in the module, all right, essentially, first of all, there'll be 2 so-called CA assignments. One CA1 from me. Okay, CA1 is from me. Then there's a CA2 from Prof. Ho. All right, and in our usual pattern, all right, CA1 from me worth 20 marks. CA2 from Prof. Ho worth 20 marks. All right, I'll say more about at least my CA in a moment. Right, CA1 from me worth 20 marks. CA2 from Prof. Ho worth 20 marks. Right, then my part, also quite usual, I will push you on to do essentially more of a project type of work, all right, and that I will call CA3, and that's worth 30 marks in the module. Okay, maybe I should also at this point say a bit more, because you would have seen that our class is a combination of 5104 students, which is most of you all. Then there are 6104 students, 8 of them, and they are 6104. Okay, at this point, let me put your minds to rest. Don't be worried at all, that, your 5104 have to compete with this 6104. No. The grading is completely separate. 5104 grading is completely based on 5104 class, 6104 grading based on 6104 class. All right, and then what will happen, all right, and you will see as I develop the material, that, okay, even the CA assignments, all right, what will happen is that the 6104 people, their assignment, we push them much deeper. All right, similarly in the CA3 project, I will also push them much deeper. But even then, there's no worry at all, because the grading is totally separate. 5104 grading is 5104 grading, 6104 grading is 6104. Right? Except, okay, I suppose it's also relevant, pertinent to emphasize to the 8 6104 students. They are PhD students anyway, right? And 2 of them are my own PhD students. Right? Welcome. Because they are PhD students, they certainly expect that they should be pushed further, right? They should be pushed further, and we also want to prepare them for their PhD, right? In the course of the module, of course, I will develop both the basic and the advanced ones, right? Then for those parts which are very, very advanced, I will still develop it, but I'll just say, okay, 6104 people need to know this for exam, all right? But 5104 people, this very, very, very advanced one is just of interest for you. So it will be very, very clear, so don't be worried. Right, then finally, examination will contribute the final 30 marks, all right? And then my students previously taking module from me, I saw, okay, Yenan is here, Jiawen is also here, they took modules from me last semester. They will also know that even here, certain things are very clear. Okay, I'll say that in a moment, but before that, let me again assure you, 5104 exam paper and 6104 exam paper are totally separate. Okay, they're totally different. Okay, and again, the 5104 exam grading is 5104 exam grading. 6104 is a different exam, it's based on their own grading. Okay, so no worries at all. But here I just want to say exam contributes the final 30 marks, right? And Yenan and Jiewen will know what I'm going to say. Because if you had taken note and you had kind of more or less counted, right? My CA1 is worth 20 marks. Prof Ho CA2 worth 20 marks. My CA3 is worth 30 marks. So I've already taken 50 marks. Right? Prof Ho now is 20 marks. So in the exam worth 30 marks, exam will have 4 questions. Mine will be question 1 and 2. Prof Ho will be question 3 and 4. Okay? And my questions 1 and 2 actually very often will be just as long and almost as difficult as Prof Ho 1. But in order to be fair to Prof Ho, when it comes to this stage for the exam, all right, my question 1 and 2, even though they are just as long and just as difficult, my question 1 and 2 only take up 10 marks. Prof Ho's question 3 and 4 takes up 20 marks, to be fairer to Prof Ho lah. Okay, but nearer the time, we'll remind you, because that is important when you are doing the exam, all right? Because then when you manage your timing for the exam, you need to remember that, okay, me, Professor T.H. Lee, my question 1 and 2 is only worth 10 marks. Prof Ho, question 3 and 4 is worth double, worth 20 marks. So you need to plan your time carefully. But we'll remind you. Okay, so then very, very quickly then again, all right, just to emphasize, okay, classes online via Zoom, but exam will be, okay, university told us to remind you all, because one or two of you all still email to us on this. Okay, university told us to remind you all, final exam will be in person, face-to-face, all right, scheduled for some classroom in our faculty, all right, so that means you need to be present. Okay, two of us, lecturers, myself, okay, I take the first part of the module, Prof. Ho takes the second part. Then, as I mentioned, right, syllabus and all that, I'll just let you read, right? Once we start the module, it will be very, very clear to you what we're doing. Okay, then insofar as assignments and grading in the module is concerned, okay, first of all, very, very clear, 5104 grading and 6104 grading are totally separate. Okay, so there's no competition between the two classes, so you don't have to be worried. Okay, then, okay, the grading, CA1 from me worth 20 marks, CA2 from Prof. Ho worth 20 marks. Then I have a CA3 worth 30 marks, exam worth 30 marks. There will be 4 questions, 2 from me worth 10 marks, 2 from Prof. Ho worth 20 marks. Okay, before I go on to say more in detail about these things, let me pause here, check whether anyone wants to say anything, any comments, any questions. Today's class will not be too long because I just want to introduce and motivate some material. Okay, but I also will go on, even though not too long, it will be almost close to 2 hours, depending on how fast we go. Okay, I'll be covering some very, very detailed material, except I don't want to push it too far because it's the first class. If I push it too far, you will all be lost. Okay, so okay, just on these things, then of course, as my students know, students who have taken classes from me know, afterwards I would tell you in more detail about my CA1 and my CA3. Even though you will not be able to start on it, at least I will tell you much more, and also on all the reference and support material that we always have available for you all in our module. Just to let you all know that you have a lot of support. You have a lot of support and a lot of material we make available in the module so that you can really do your CA well, both the CA1, CA2, and also the CA3. Okay, anyway, before I push on, let me pause here, check. Any comments, any questions? Okay, there's one question in the chat from Liu Wanze. Okay, Wanze and everyone. Okay, the project, I don't mind, as I also told my students, because I told you in 6104, my 2 PhD students are here, Guo Hao Ren and Wang Jiahui. I've spoken to them before. I said, look, you know, when you do the work, I don't mind you do it together, you discuss, okay, because that's the whole nature of the real world. When you go out to work, it'll be like that, okay, but even though you discuss, okay, and then you maybe even do some parts of the project together, okay, but finally when you write the report, okay, every report that you write must be each individual person's report, okay, because you don't tell me that, look, you know, 2 of you had worked together and discussed, you know, then I say, okay, after you discuss, it's fine, but you must write individual report. Okay, then you don't tell me just because you discuss and you are so good friends that even when you individually write the report is exactly the same. Come on, you know, so look, you know, and then when you submit it to the Luminous, you will check for similarity. You know, if your similarity is 90%, 100%, you are really, really in trouble. So Wanze, yes, no problem, Wanze, and everyone, all right, even though Wanze is the person who asked the question. Okay, I don't have a problem if you all discuss and work together on the project. I don't have a problem at all. Okay, just that, okay, our requirement is that finally when you write the report, okay, we want you to think deeply on your own and write your own report. Okay, Wanze, clear or not? Okay, okay. Okay, then as I said, today will not be so long a class lah. Then before I forget, as I said, my own students are here. Okay, after today's class, okay, I wouldn't hold the rest of you. All of you can just go after we finish. You can just go and do your own thing and start enjoying your weekend. But I do want to request my own students, after the class is over today, please stay back for a little while. I want to talk to you all. Okay, so certainly, Hao Ren and Jia Hui, please stay behind. Then also, I have MSc students. I have MSc students working on MSc project with me. Okay, and my MSc projects, basically, they work with my young colleagues now, even though I am the main supervisor. Okay, so I know who is supposed to be here. So I'm going to say your name. So afterwards, please stay behind. I see Howren respond already. Jia Hui respond. Okay, I'm supposed, my other students who are supposed to be here, MSc student. Okay, first two working with Dr. Chen Guorui, one working with them. Huang Chen Chen. Okay, Chen Chen, make sure you stay behind after class. And the other one is Yin Si Yang. Okay, Chen Chen Si Yang, remember, stay behind. Then some more, I've got also one more student in this class working together with another young colleague, Dr. Huang Sunan. Fu Yalun, Yalun, you're supposed to be here. Yalun, please stay behind as well. Okay, after today's class, then three more students working with my young colleague, Dr. Liang Wenyi. The three students are Feng Sijia. Okay, Sijia, I saw you in the list already. Hua Sibei, I think your computer took a long time to get in, but I saw you got in already, so please stay behind as well. Then of course, Jaewen, okay, please also stay behind. Okay, with that, let me now go on. All right, so those of you whom I say just now, okay, I saw that. Please stay behind. I just want to at least touch base with you after the class. Okay, but of course, the rest of you all, if let's say you want to stay behind because you have additional questions, you're welcome to, because as I say, I'm not in a hurry to run away. Okay, with that, okay, as I said, I will go on, all right, to talk more in detail about all these CA assignments and everything. Okay, but before I do that, let me go to, first of all, the announcements, right? So you see I posted the announcements, okay, which I reposted again. So Zoom classes, right? Then you will see shortly, all right, that I will use the basically the Note01 file. Okay, it's here. Okay, what I'll do is I will, you will see that what you are able to download, many parts are still missing, right? Many parts are still missing. And afterwards, I will begin to write into it in detail to develop the material. All right, so as I mentioned, I'll start doing that. Okay, so we'll use that, and you will see, well, my students know, Yen Han, Jaewen noticed that way I would do my classes, because when it comes to very, very detailed mathematical material, it makes no sense to just show PowerPoint after PowerPoint. You wouldn't learn anything, all right? And you wouldn't even know what's happening. So I would do everything by hand. Okay, I'll do everything by hand, but what will happen is that after we finish the class, everything that I do by hand, I will upload it, because some of you will be worried that you missed something or something like that, okay? Then, okay, you know, even though whatever I do carefully. Next week's class, when we start, I will carefully do a lot of revision before we start, so that to make sure nobody is left behind. Okay, and of course, the thing is recorded on Zoom, so you can also see the Zoom recording. All right, so then the other thing that I want to mention is, right, as I said, okay, for our module, all right, we prepare things very well, and we prepare things very carefully. All right, I have my GAs. All right, when it comes later on to what we call the E-Lab sessions, all right, my GAs will guide you in detail. All right, and they will brief you in detail and even give you a demo. Okay, afterwards I'll describe the CAs, all right, and the E-Lab. All right, but I have very well trained GAs, all right, my own PhD students, all right, who will guide you. Nearer the time, I'll say more about it. Okay, if for you to basically start your own planning, all right, start your own planning, okay, start your own planning on taking care of planning your time. If you go to our conferencing, all right, some things you would already see. Okay, so the all these there are programmed my classes, class 1, 2, 3, 4, 5, 6, right? Okay, but then after that, straight away you see that I've already programmed the E-Lab class. Okay, the E-Lab class, the first E-Lab session, both the E-Lab sessions are during the recess week. Okay, during the recess week. So the first E-Lab session is on Monday of the recess week, 2 p.m. to 5 p.m. Okay, where my GAs will carefully guide you, as I say, through the E-Lab, right? Then I make another session, okay, and in this second, usually by the first session, most of the things will be clear to you. But what will happen is that the second session is also very useful, and that will be on the Tuesday, also 2 p.m. to 5 p.m., right? And what will happen is that during this second session, all right, my GAs will brief you then on some suggestions on further ideas on how you may do better in your CA report, your E-Lab report. All right, and of course, you also can come back in case you have whatever questions that you want to ask them and double check with them. So, okay, so you can see, so you may want to take a note and begin to put that in your timetable. Okay, I'm also aware that this time may not fit everyone. Okay, I'm aware this time may not fit everyone, but never mind, let me put it down here first. Okay, my GAs are very well trained by me. They are answerable to me, okay, because I directly talk to them. Okay, so if it turns out that both these sessions, the timings are difficult for you, no problem. All right, nearer the time, I will remind you all, what you do is you simply email to my GA, copy to me, all right, to ask for alternative times. All right, and no problem. All right, they will just check, maybe a few of you email, then they will find a common suitable time for the few of you, and they will set up extra sessions. All right, so no worry. All right, even though I've programmed this down here so that at least most of you will be able to make it, okay, and then at least we can proceed in a very, very organized fashion. But those of you who cannot make it, no problem. You just email my GAs, all right? You want to see my GAs, they are here under module details, under facilitators, right? Dr. Wang Wensing, Ms. Zhang Xiaoxue, Mr. Chen Zhilong, right? So I have 3 of them. They are all answerable to me. All right, they are all answerable to me. So no problem at all. All right, you can see in there how to email them as well. All right, so nearer the time, if these times do not fit you, you can email them and we can easily program alternative sessions. All right, then in this same way then, okay, there are some of you, all right, and indeed, you know, every year is like that. There are some of you who, even though you can make, you can make it for this first session and second session, but you want even more sessions, you want another third session or fourth session. So it's the same. You just email them. Then, you know, similar to all the other emails they receive, they collect together enough emails, they'll set up those additional sessions. Then it will all be possible. Right? Okay, so that's insofar as the schedules are concerned. Right? So as I said, I just wanted to mention this today, the fact that I have very, very well-trained GAs. All right, and they are directly responsible to me, so you will be guided very well. All right, and then there's flexibility also for those sessions. Right? Okay, so then with that, then okay, you would also have noted all the materials in the file. Okay, so with that, let me then go on. All right, to talk about to talk a little bit about the actual details of these CA assignments, even though you are not completely familiar yet, but let me say a little bit about the details of these assignments, all right, so that you know how much reference material we will be providing you, all right, so that you really can do your work well. All right, as my students know, my students who are here, they know we provide very, very detailed support material. Okay, but never mind, before I go on to that, let me again pause for a while, check anyone wants to say anything at this stage. Okay, so I saw the reply here from Hao Ren, from Jia Hui, from Jie Wen, from Si Jia. Okay, I just want to remind the other few again. Si Bei, okay, Si Bei, I need you to stay behind too. And then, okay, that's those with Dr. Liang Wenyi student. Fu Yalun with Dr. Huang Sunan, my student. Okay, Yalun, I need you to stay behind. Then Huang Chen and Yin Si Yang, my students with Dr. Chen Guorui, I need you to stay behind as well. Okay, but meantime, the rest of you all, anyone has, okay, Si Yang replied, Si Bei replied. Okay, the rest of you, anyone has any other questions? Okay, Si Yang, Si Bei, Yalun, okay. Okay. Zhao Qi, Huang Zhaoqi asked, what is the meaning of ELAB? Okay, you just wait a while, it will become very clear. Okay, because I'm going to describe the CA assignments. Okay, it will be very clear. Just wait a while, Zhao Qi. Okay, any other question? Okay, if not, then let me exactly now. All right, so as I said, if you go to right, our files, the work bin, you go to my section. Okay, so if you go under assignments, right, you will see I provided some material. I've given you a sample of the 5104 CA1 description. Then I also show you a sample of previously what we asked the class to do for my CA3 mini project. Okay, so I'll describe that in a moment. All right, first of all, let me show you the CA1 sample first. All right, because you can download it from here. So let me show you something, okay? And this is the 5104 sample. Never mind, here what I've done is I've actually put the 6104 sample, okay? So it's not exactly the same as in the file, but you know, it will be the same kind of idea lah. So this is the CA1 right up. All right, after you studied adaptive control, you will be able to do these things. Then, okay, what you have down there is probably quite close to the original. All right, but I will change the numbers every year lah. So never mind. So basically, okay, this is 6104, right? So I changed the numbers that year 2017, 2018. So this is what I asked you all to do. All right, after you've learned the material, go and actually simulate the actual adaptive controller. All right, so you simulate the adaptive controller, and essentially, what happens is that I think for the 5104 one, I think it stops here. 5104, it stops here. All right, then 6104, I push them further. All right, because I asked them to do these additional things. The additional things actually for 6104 are simple to do. They're not difficult, except that, you know, after you do these things, I want you to think about it and see what you're observing and tell me what's happening and analyze for me what's happening. That is the deep part. Okay, but 5104 end here already. 5104 end here. 6104, these are the deep parts that end here, and then I want you to go on. All right, so this one is basically just then a simulation project. All right, the easiest, by the time you have understood the material, okay, for this one, CA1, you will not be able to start on CA1 until I have finished lecture 5. Okay, you need to finish lecture 5 before you can start on your CA1. Both 5104 and 6104 people. Okay, actually CA1 theoretically is the more difficult thing. Okay, but never mind, it's just a simulation project. So simulation, I leave it to you. All right, I would imagine that many of you are familiar with MATLAB. All right, you can use MATLAB to program this. Actually, if you are even familiar with the graphical version of MATLAB, okay, Philip, I will also talk about the deadline very, very soon, Philip. I'm aware all of you all are very worried about all those things. I'll speak on that very, very soon. Okay, okay, this is simulation. As I said, well, MATLAB, all of you are familiar, right? So this can be programmed easily in MATLAB. But actually, if you are familiar with the graphical version of MATLAB Simulink, then it makes it even easier. Okay, but I leave that to you. So you can take any programming language you want. In fact, at this point, I will even say one interesting story. In the very, very early years, all right, one student even completely programmed this in the C language. All right, he's a very hardworking student. In fact, later on in some of the parts, you will see his name coming up, right? His name is Lin Feng. So I spoke to him. I said, Lin Feng, why are you so hardworking? Why are you programming this thing in C? I mean, life is very hard, you know, to program in C. Then he answered me. He said, Prof, I want to program this in C because later on in my actual work, he works on UAVs. All right, he said, later on in my actual work, I want to be able to use these adaptive control ideas in my real work. All right, if I program this in C, then all my program is ready. Okay, so as I said, you know, we leave it to you. Whether you want to program in MATLAB, Simulink, if you want to do in C, that's also fine. Okay, so that's CA1. Okay, let me show you CA3. Okay, and that will answer Zhao Qi's question shortly. And immediately after that, I should remember Philip to talk about deadlines. Okay. Okay. For CA3, before pandemic, we used to force everyone to go to the lab and really implement all of these things, the adaptive control, really on the motor in real time. This is LabVIEW, you know, really running in real time. Okay, and then you see this is a LabVIEW program, programming the calibration, then right, the LabVIEW part, programming the full adaptive controller in real time, running in real time. Okay, and LabVIEW is very similar to Simulink, right? LabVIEW is basically the real time part of Simulink. Okay, so to answer Zhao Qi, the reason is this. Okay, because nowadays, you know, we have to minimize actual happenings in the lab, particularly in the last year and the previous year, all right? And then this year we thought, okay, we still carry on. So carry on in the sense that we convert all of these things to simulation. Okay, so Zhao Qi, what this means is that whereas previously it was really in the lab on the real motor, okay, on the real motor, okay, so now because, you know, it's more difficult to schedule the real lab. So even for this year, we decided that even though your CA3, you will still be doing something similar, all right? But we converted everything to simulation, all right? So that is what is meant by ELAB, Zhao Qi, in the sense that you're still doing exactly the same thing, but now everything is converted to simulation. But you will be basically, you know, experimenting with the same thing. I would expect that, you know, you would really simulate the motor properly for me with its saturation bands, with its dead zone and noise. All right, and then work out these equivalent things, except that it's no longer in LabVIEW, it will be in Simulink. Okay, when I actually upload the actual real, so you see down here, I said this is just a sample. Actual assignment, I will release at a later time. When I release the actual assignment, all of you, you will see that, okay, we've now converted it to simulation. But basically, it will be completely equivalent, right? It'll be completely equivalent. Then I will ask you all to explore the thing and show us. Okay, then I want to go on to show these next two documents. All right, but before that, before I forget, okay, one moment. Okay, Wendong is worried about motor control. Don't worry, Wendong. Don't worry, okay? Once I tell you a little bit more about these two very, very detailed files I'm providing, first of all, there'll be a lot of information. But also, Wendong, you don't need to know in detail about motor controller, because whatever it is, if you are going to do a control systems module, and this is a control systems module, you should be able to control anything we give you lah. but specifically the details of motor control, it is not important to know. Okay, but don't worry, afterwards, when I show you these two very, very detailed files, you will also see that you don't need to be worried lah. Okay, but let me, first of all, before I forget, answer Philip's question first about deadlines. Okay, my students who have taken modules from me before already know what I'm going to say. So Yanhan, who is here, Javen, who is here, took module from me last semester, myself and Prof. Ho also. So our practice is always the same. We are very, very kind people. Okay, we are very, very kind people. So Yanhan and Javen knows what I'm going to say. Okay, whoops. No, I don't need this. Knows what I'm going to say. All right. Okay, maybe let me pull this down here. Okay, so you see how we program it. We program it so that basically, you know, you're starting to do both your CA1 and CA3 during recess week. Okay, during recess week. Okay, so as usual, with Prof. Ho and myself, we are very kind. All right, so your work is done during recess week. Then what we want now, is for you, don't try to rush and finish your work. No, we don't want you to rush and finish your work. We want you to do your work and then think about it. All right, and that's why I say some of the students, they even want to come back for session 3, session 4. We want you to think about it. All right, and then see how you can even further improve it. All right, and so we really want you to think more and more. But because of that, we also give you a lot of time to write. Okay, so the deadline to send in the report will be, so you are doing all these sessions during recess week. Okay, recess week. The deadline to submit the reports will be in reading week. So reading week is the week just before exam. Okay, recess. So remember, before recess week, we have 6 weeks of classes. Then there's recess week. All right, then there's week 7, week 8, week 9, all the way week 13. Then recess week really is the week after week 13. So okay, in answer to you all, we give you, okay, more than 7 weeks to write your report. Okay, and it will be the same for Prof. Ho 1. Okay, so we are very, very kind, very, very kind. Okay, but yeah, Philip, you are correct. Philip, you are correct. Okay, so on the one hand, you can say we are very, very kind lah. Okay, the flip side of the coin is that, look, since we give you so much time to write your report, our expectation is that you jolly well think very deeply, do very good work, and give us very, very substantial reports. Don't give me 2 or 3 pages report, because, you know, I can tell you there will be some other in your class who are, you know, they really work very hard. They will give 30, 40 pages report. And if your report is 2 or 3 pages, and the other one is 30, 40 pages, I don't even have to say anything. Who is going to get the much more marks? There's nothing for me to say, right? It's very, very clear. Okay. So on the one hand, we are very, very kind to give you a lot of time, but it also means that we expect you to think very deeply and do your work well and write your report well. Okay, but don't worry, because I want to come to my next part. All right, which is this part. All right, which I promised Wentong to say on it. So, okay, if you see these 2 other files, okay, this is a very, very detailed CA1 briefing note file. This is a very, very detailed CA3 briefing note file. Okay, the earlier two files, this is just a sample one page that you saw, all right, which describes typically what my description of CA1 will be like. Then you also saw I showed you the briefing notes of CA3 file. So you see Lin Feng down here, I told you about Lin Feng. They were my early GAs. He was the one that programmed everything in C. So okay, this is a very simple CA3 briefing file. It's a simple one, all right, but will enable you to get started, all right, because you are simulating all of this now, all right, but it's very similar. All right, it's a simple one. Okay, then what happens is that in later years, I had a very, very good GA. Okay, so Yanhan and Jaewen will know this was exactly the same thing I told them last semester. I had a very, very good GA in later years. All right, his name was Sun Lu. Now he's got his PhD. He's working in A-Star now. Okay, and Sun Lu was very, very hardworking and very, very good. So I told Sun Lu, I said, Sun Lu, since you are so hardworking, can you write a very, very detailed CA1 report or not? All right, and write a very, very detailed CA3 report because it will help the students. All right, because you know, with this very detailed CA1 report here and this detailed CA3 report, all right, as I always typically tell the class, I say with what Sun Lu has done for me in this detailed CA1 and this detailed CA3, which you can download, with these things down there, pretty much, all right, almost 50% of your CA1 and CA3 report is already done, pretty much, okay? Because, you know, Sun Lu has given you a lot of details in there for you to really get going on your CA1 and CA3, okay? So that's a good part. But what that also means is that, look, you know, if in your report, all you do is you mostly copy from what Sun Lu has done and give that to me, compared with another person who basically, okay, I mean, this helps you get started. Another person who builds on this and does much more new and original things, you know the difference already, okay? But at least with these things, right? At least with these things, you can easily get started. Okay, and I'll show you these things now, okay? So remember, as I said, you know, the CA1 description is just like this. All right, then you go to what Sun Lu has done for me. Okay, this CA1. So you see Sun Lu, okay? Sun Lu has done for me in detail describing CA1 43 pages. All right, basically describing everything that in the lectures we'll cover all of these too lah. All right, but Sun Lu has described nearly everything to get you started. All right, Sun Lu has even given you a schematic to get you started on your MATLAB Simulink. Okay, so I have a lot of reference material to get you started on my CA assignments. Okay, so the idea is to help you. But as I said, you know, it helps you get started. Okay, but you know, there will be many students in the class who, after starting that, they will do their own original things and new things. So everybody needs to be clear. If all you do is, you know, just cut and paste from Sun Lu, you're not going to be very well off. Huh? So this CA1. All right, similarly, you will see that, so that also will typically, right? So this is CA3. Okay, you saw the other CA3, the simple one, which is from the early days by Lin Feng they all, right? So you can see, right? This is quite a simple one. But you see that later on, okay, I told Sun Lu to write a very detailed one. So you see, even for CA3, Sun Lu has written nearly 60 pages. Again, in detail. All right. So you will be simulating all of this. So this is the answer again to Zhao Qi, right, on ELAB. Okay, so you'll be simulating all of this now. So all these things can be simulated, but I give you enough, all right, enough supporting material to get you started, all right, and it's all already inside our Luminous. Okay, it's all inside our Luminous. Okay, so here I believe I've answered everyone's questions already. Okay, so now let me, before I start, okay, today we will not have a break. As I said, you know, I will finish within 2 hours. Okay, let me go back to the README first file. Anyone has any comments, any questions at this point? Okay, okay. With that, then we're going to start. Okay, as I told you, I will start. All right, I will start with the Node 01 file. All right, the ideas here, all right, in some ways are very direct. All right, you could even say the problem that I put down here, you could even say it's a simple problem. All right, but even though the problem is simple, the ideas here are very, very important because basically, all right, basically these are the key ideas. These are the key ideas that you need to learn them well. And when you learn them well, even though this is a simple problem for now, later on, when we begin to look at more and more complicated ideas, you need to understand these very simple ideas first so that, you know, whatever is described of the complicated ideas, you can see why it is in that way. Okay. Okay, so okay, I see a comment down there from Yichen. Final exam, open book or closed book? This part, I will tell you lah. Yichen, we haven't decided yet lah. We haven't decided yet. Nearer the time, once we decided, we will tell you all. But we will tell you all with enough time ahead lah. Because some of the things we also don't really know how to think about it. Because you know, in the last 2 years, it had to be exam which is invigilated over Zoom. So since it's invigilated over Zoom, it's totally different. So we had to adopt different rules. But now it comes back to the classroom as in person, face to face. So we haven't decided. So Yichen, don't worry lah. Don't worry. Okay, whatever it is, we will tell you all ahead of time. Okay, with that, let me start. So as I said, I will want to, in some ways, all right, look at this so-called extremely simple problem, but yet the ideas are very deep. Okay, so let's start. Okay, so basically with this then, right, what we're saying here is, okay, let's look at the usual method, right? Let's look at the usual method. Okay, let me begin to. Okay, let me begin to motivate the subject. All right, motivate the subject by saying, look, you know, this is a very typical control problem that you would begin and you would start and look in the beginning, right? So, for example, you might want to say, look, you know, I want to control a system like this. And typically the system that we're controlling, we will say this is the plant, all right, meaning a manufacturing plant or whatever they're trying to control. But never mind, let's call this the plant. All right, and let's start with the simplest kind of system that we want to control. And we start with a very simple first order system, right? First order system. All right, yp dot equals to apyp plus kpu, right? Where yp is the output of the system you're trying to control. U is the manipulated computer control signal that you can put in. And let's say this system is like this. All right, so as a start, let's consider this very simple case. All right, and typically, right, typically what would happen is you would say, look, I want to control this. I want to control this. And then a lot of times, you know, when you say you want to control something, you have some kind of a specification. You have some kind of an expectation to say, okay, you know, after I finish controlling this, I would like to have a situation whereby, you know, if I put in a command signal, okay, a typical command signal might be a step signal, right? I expect that after I finish controlling this, when I put in a command signal, I expect that, okay, the thing that I finished controlling should give me a response that is something like this. All right, quite typical. All right, no steady state error. All right, and then it must have a certain rise time, which tells me how fast, after I control the system, how fast should the system respond. All right, quite typical. Okay, then, okay, let's look at this system. We say, okay, we're controlling this first order plan down there. All right, very simple, very simple first order plan. All right, and then with this kind of expectation, with this kind of specification, all right, simple plan. All right, if you say you want this kind of performance at the end, all right, pretty much for this first order system, if you say you want that kind of a performance, pretty much you are actually telling me, right? You are actually telling me that, look, you know, you want to match a closed loop performance, something like ym dot equals to am ym, all right, plus km times r of t, all right, where, all right, the am down here obviously is a negative number, because if you say you want this kind of response, all right, basically it's a stable system, right? It's a stable system, and the value of ym will tell me how fast you want the system to be. So basically this is pretty much is your system given to you. You say you want this kind of performance, pretty much is what you're saying. All right, then, you know, if you want something like this, okay, at this moment, we're not doing adaptive control yet. We're not doing adaptive control yet. We're just saying, look, you know, you give me a system like this, in the end, after controlling, I like to have this kind of performance. Then you look at this and you say, look, you know, for this simple system, okay, I know what to do. All right, I will take the y, I will feed it back through a gain. I will take the reference command signal. I will pass it through a scaling gain and put it in down there. So basically what we're saying is that, look, you know, if you want to now, with this open loop system like this, and if you want this kind of similar performance, basically the control signal, all right, the control signal that works for you, all right, the control signal that works for you will be u equals to that gain theta times yp of t, all right, plus the gain k times r of t. All right, so it's as simple as that. So here we're not doing adaptive control yet. We're not doing adaptive control yet. We're just saying, okay, what is the thing that we will do? All right, and once we noted that, let's begin to carefully develop the equation. So this is the control signal that we need to use. Okay, so let's use the control signal. So we use the control signal. All right, we use the control signal kp theta times yp of t plus k times r of t, exactly as we said. This is the control signal we use, right? Okay, and then quite simple. We take the whole thing, we rearrange, right? We rearrange, and basically now when you rearrange, you are now basically, after you rearrange, you're basically saying, look. What you really want is you want this, right? You want this to become am, and you want this to become km. All right, so that's exactly it. Okay, you basically need to find that theta, all right, to make this am. So that specific theta that makes this am, we call it theta star. All right, and you want to find that specific k, all right, to make this km, that specific k that makes it kpk equals to km, we call it k star. So these are the so-called, if you like, the perfect gains. All right, and if you exactly put the perfect gains in there, all right, if you exactly now here, all right, instead of putting some general theta and general k, if you exactly put theta star and k star, all right, if you exactly put theta star and k star, all right, you then know that, all right, you then know that with that, this now, clearly now, when you write it out, it becomes exactly am yp of t, all right, plus km times r of t. All right, because that was how those perfect gains were actually specified. All right, so we have that. Okay, so once we have that, when we put in exactly those perfect gains, theta star and k star, we have this. Okay, then let's check the tracking error, because in any case, you know, to begin with, we were interested in the tracking error, right? We're interested in the tracking error. Okay, we're interested in the tracking error, this which is yp minus ym. All right, so let's see. Okay, if you put in exactly theta star and k star, all right, let's see now what's happening now with the tracking error. All right, so with the tracking error is yp minus ym. All right, so E1 is YP minus YM. So E1 dot is YP dot minus YM dot. But now if you put in the perfect gains, theta star and K star, all right, then YP dot is just AM YP plus KMR. YM dot was already AM YM plus KMR. Then obviously now, okay, with the perfect gains, all right, this just reduces to E1 dot equals to, right, AM E1 of T. And remember, by choice of your reference model, right, by choice of your reference model, AM is actually a stable system, all right? So you clearly see that, okay, in this simple arrangement, all right, the tracking error dies away, right? Tracking the error dies away. Okay, this is where we can start thinking about adaptive control, all right? Because now, in all of the above, we work along the way and we said, look, you know, you get me the perfect gain, right? You get me the perfect gain, theta star and K star, right? You're supposed to put the perfect gain theta star and K star in here, and then you saw what happened. Okay, and this is where adaptive control can start, because, you know, in the system, we then say, okay, it's the same arrangement. It's the same arrangement, all right? It's the same arrangement that we now want to look at, except now we do not know AP and we do not know KP. We do not know AP and we do not know KP. And yet, we still want to exactly get this same result that, you know, E1 dies to 0. We want to get the same kind of result. Okay, so we do not know AP and KP. And this is where adaptive control starts. All right. So since we do not know AP and KP, it's not possible now to calculate theta star and K star to put into the system. So instead, let's do the following. Okay. So first thing is we say, okay, we do not know the values of AP and KP, which means we cannot exactly calculate theta star and K star to put it in. But we go back and we said in this arrangement that we are looking at, all right, in this arrangement that we're looking at, all right, we know that this control law works. We know this control law works, except that when we know exactly AP and KP, we could put theta star, we could put K star. All right, but now we don't know AP and KP, we cannot put theta star and K star. But this control law works. This control law works. Okay, so if that's the case, since the control law works, all right, I'm going to use still the same control law, except that because I don't know how to exactly calculate to put theta star here and K star here, I'm going to make these control gains here, both of these control gains, I will make them time varying. And now that I made them time varying, I have to tell you how to make them time varying or how to adapt them. And that's essentially one starting point of adaptive control. All right, that's one starting point of adaptive control. So as mentioned down here, we don't know AP and KP. We cannot therefore calculate exactly theta star and K star. All right, but we know the control law works. All right, so we said, okay, we know the control law works, therefore we will still exactly use the same control law. It will still be theta YP of T, all right, plus K times R of T, because this control law works, except that because we don't know how to calculate exactly for theta star and K star, we said we're going to make this now time varying. All right, and okay, since we make them time varying, we have to tell everyone how we are going to make this time varying, i.e. how we're going to adapt them. So how are we going to adapt them? Okay, at this point, I'm going to write it down almost as though it's like magic, all right? But it is not magic, okay? There's a systematic procedure to it, which later on will come up. Okay, so as I said, you know, first thing to do is we know the control law works, but we don't know how to exactly calculate for theta star and K star. So we make them time varying. Okay, then we have to tell people how we are making this time varying, or how, all right, we are adapting this. All right, so we tell them Wendong and everyone, don't be in a hurry. All these things about deep learning, all those things, you know, they are all there. All right. Some of it in deep learning is good. Some of it in deep learning, I'm not convinced myself. But this one, all right, this one, Wendong and everyone, what we are doing is completely rigorous. It is completely mathematical. It's not like, you know, guessing. All right, not like guessing and hope it will work. No such thing as hoping. This is guaranteed to work, and that's where the difference is. Okay, so don't be so excited to go and start talking about deep learning and all that. Similarities will come, but don't hurry, Wendong and all that. Okay, so how are we going to now adapt this? Okay, as I said, you know, these things are a lot deeper than, in some ways, you could even say some of the ideas in deep learning and all that, borrow some of these ideas down here. But never mind. Okay, so how are we going to make this adapting? Okay, so as I said, I'm going to just write this down. I say, okay, you adapt them in the following way. All right, because you know, you got to tell me how to update data. I say I will update data in the following way. All right, I'll update data in the following way. All right, you go and take the tracking error. You can measure the tracking error because you know your system output is YP. The reference model that you say you want to get the performance is something you generate. So you have YP, you have YM. So I put the tracking error down here. You can measure YP, so you put a YP down here. Then I put a gain down here. And the only requirement for the gain here is that it should be a positive number, no other constraints. All right, not like some of the so-called stochastic learning, deep learning, where some of these gains must be sufficiently small, and you don't even know, you know, what is sufficiently small because it has to be some kind of incremental or whatever. No such thing. Okay, what I'm doing here, my only requirement is positive, and I'll show you perfectly how it's completely guaranteed mathematically to work. All right, so this is theta, okay, E1, YP, gamma 1, just a positive number. Okay, in this way, first way that I'm doing it, even though I don't know the system completely, I need to know the sign of the K parameter. So I put signum KP here and minus. Okay, but it is not difficult because, you know, in some deeper work, even not knowing the sign of KP, you can get around it, okay? And this was some of my own PhD work many years ago where I can completely remove this sign, okay? But never mind, for this simple one, I just show you, okay? I put this down here. And it's not difficult because in real life systems, let's say in your motor, to know the sign of KP, you just put a positive step to see whether the motor turns positively or negatively, and you got the sign of KP, right? Okay, so but never mind, for this simple one, we keep it this here, that, right? Then for the K parameter, all right, you also put E1, then you put the reference signal, because the reference signal is given by you, you have it. Then I put a gamma 2, also any positive number minus signum KP, and I put it down there. Okay, and I say you adapt it in this way. Okay, you adapt it in this way. Okay, if you are curious on what this means, okay, you can easily put this together in a Simulink simulation. All right, in fact, I would even say, you know, after tonight, when we finish everything, all right, for those of you who are really excited, go and take a simple system, simulate a simple system like this, put it down here. All right, and then choose a stable reference model like this, put it down here, put it there. All right, and exactly go and use Simulink to put it together, because later on when you do your CA1 and CA3, you have to do it anyway. So I would say even now, after we are finished tonight, all right, you exactly go and program this in Simulink, and you will now know exactly what I mean. It's very easy to program in Simulink. You just take the E1 signal, then multiply by the signal YP, put a positive gain, put whatever you have as the sign of KP, and then you update this as theta dot. You update this as K dot. All right, and you're finished programming. Except that here it is not. You hope it will work. No. Okay. In the next half an hour or so, I will show you perfectly how it is guaranteed to work. Okay. So the point is, how does this work? How does this work? Okay. First thing to do is to note that hey, which is some of you wrote to me. You said, okay, you know, you didn't have the prerequisite. You know, you didn't have the prerequisite of linear systems, and you say, oh, you know, in your undergraduate, you studied signals and systems, which is basically, but I said, never mind lah. Come, join the class. Because, you know, later on, even today, even by tonight when I'm done, you will have to decide for yourself and think for yourself whether really your so-called signals and systems is enough or not. Huh? Because, okay, what will happen here is that even though this looks like your undergraduate starting point for control, the next thing that I'll do will be nothing like your undergraduate control systems, because, okay, the ideas from undergraduate control can no longer work, okay? So if the whole arrangement will be like this, all right, we said the control structure works, so we use the same control structure as we said, all right? So we use the same control structure, all right, except we made the gains time varying. And since they are time varying, we now have to say how we are going to adapt them. So this is how we adapt them. Then the next thing is we now need to answer how this works. All right, so all your undergraduate things, you know, on undergraduate control, I'm sorry, it will not work already, because to begin with, this is no longer, you can no longer look at left half plane, right half plane, frequency, domain, root locus. I'm very sorry, none of this works anymore. Okay, instead, okay, because none of this works anymore, we have to look carefully at what we have and say, okay, to be able to study this, perhaps the first step is to say, what are the signals that we are interested in? Okay, clearly the tracking error we are interested in, because we want to make sure it goes to 0. Okay, then clearly the control gain associated with y, remember we said u equals to theta typ plus kt times r. All right, so this is the control gain, which is time varying. We're interested in that. So even though we call it a control gain here, but you better think about it, it's just another signal. Okay, it's just another signal, because and basically you're even going to adapt it. So even though we call it a control gain, you better be interested in this signal called theta of t. All right, and per se, we're not interested in theta of t. We're interested really in what is the difference in theta of t from the exact perfect theta star that we want, except we don't know theta star. We don't know theta star, but even though we don't know theta star, there's nothing to prevent us from saying we're interested in this signal, theta t minus theta star. All right, and we call it phi of t. All right, we call it phi of t. All right, this signal. Then in the same way, I'm interested in this signal called c of t, all right, which is the difference between the signal or the gain, the time varying gain k of t and k star. Even though we don't know what is k star, but yet I can define these signals. Okay, so we're interested in these signals. All right, and because we can no longer use left half plane, right half plane, root locus, okay, the next step that we're going to do is we say, okay, we're interested in this signal. Okay, and we are interested in how these signals are behaving. So if we are interested in how these signals are behaving, one thing that we might want to track would be a so-called energy function like thing. It's not really an energy function. Or it's not really an energy function, but you know, it is basically it is ellipsoid in n space. This is in tree space, all right, because I have tree signal. All right, I just want to see this ellipsoid to see how this ellipsoid is behaving in time. All right, so clearly, as I said, we're interested in those signals. So clearly, I'm interested, therefore, in, all right, E1 squared, all right, plus, and of course, I'm interested in plus. So I say, remember, I've said it's essentially an ellipsoid, phi squared, all right, and then plus, of course, c squared of t. All right, except that because I use different gains, gamma 1, gamma 2, in my adaptation law, all right, it turns out that just by taking this three-dimensional, in this case, without changing it, it's just a spheroid, right? But the spheroid wouldn't work. I need to kind of reshape it. So it turns out that ellipsoid that I'm interested is magnitude of Kp, all right, over gamma 1. Remember, gamma 1 was the gain for theta dot. Then again, magnitude of Kp, all right, over gamma 2. All right. Okay, so this is, okay, at this moment, I don't have to actually use this in the programming. I don't have to actually use this in the program. All that I'm using this is in the analysis to help me understand what my adaptive controller is doing. All right, so I'm interested in this ellipsoid, and in particular to see how this ellipsoid now is behaving in time. All right, if I'm interested in seeing how this ellipsoid is behaving in time, what this says is that, okay, clearly I'm interested in the time derivative of this ellipsoid. All right, how this time ellipsoid is changing with time. So, okay, it's quite simple. It's quite simple, right? This is just a spheroid in 3-dimensional space. So if I take the time derivative, it just turns out to be E1 dot, all right, plus magnitude of Kp over gamma 1 phi dot, all right, plus magnitude of Kp over gamma 2 c dot. Okay, that's the first step. Then let me now check everything very carefully. All right, let me check everything very carefully. First of all, let me check E1 dot. All right, E1 dot, I can go back to my earlier expression. E1 was yp minus ym, so E1 dot is yp dot minus ym dot, right? And then what is yp dot? Yp dot was apyp plus kp times u, all right, kp times u. But what was my u? All right, my u was basically theta t times y plus kt times r, except I'm going to separate it out. All right, I'm going to separate it out by writing it as, all right, this is theta, but I'm going to separate as writing it as phi of t plus theta star. All right, and you can check that this is correct. And then similarly, k of t, I separate as c of t, all right, plus k star. Okay. Okay, then all right, the thing that you can easily note, all right, you can easily note is that, look, you know, why I separate out in this way is because this k star, this theta star is here. If I now take this AP k times theta star and the yp is common down here, I collect them together, and this kp k star together, all right, you will see that AP plus kp theta star is exactly am. Kp k star is exactly km. Okay, I'm not using this in my programming. I'm just using this in my analysis. Okay, so with that, then I leave you tonight, after you go home tonight, to double check that this now simplifies to, all right, this now simplifies to am E1 of t, all right, plus kp. Okay, I separate out this now phi of t, yp of t, all right, plus c of t times r of t. Okay, I'll let you go back later tonight to double check that this simplifies to that. Okay, that's the first part. Because as a result of checking how that ellipsoid, the ellipsoid, all right, in 3 space, how that's changing with time, I look at this ddt, it turns out to be like that. I've looked at this first set of expression. Now I'm going to look at this second set of expressions. All right. Okay, second set of expression has phi dot and c dot. All right, it's very easy to see that phi, remember what was phi? Phi was theta minus theta star. So phi dot is actually theta minus theta star dot, but theta star is just a number. It's just a perfect number. It's just a constant number. All right, so theta star dot is just 0 because it's just a number. All right, so phi dot is exactly theta dot, which means that phi dot, all right, turns out to be exactly the adaptive law for theta dot. Similarly, c dot turns out to be exactly the adaptive law for k dot. All right, and then with that, then I know I've got already the rest of the parts in this expression, and I proceed on further. Right, I'm not done yet. I proceed on further. All right, with that, I substitute them back, all right, into my v dot expression. So remember, with my simplification earlier, E dot had become am E1 plus, right, KP phi times YP. All right, then the other one was KP, right, C times R, right? So I have that. Then this other ones in there, all right, this was just going to be just minus signum, because this was just theta dot minus signum KP, right, gamma 1 YP times E1, all right, and that was just K dot, which was minus signum KP, all right, gamma 2 R times E1. Okay? Okay, so all that I've done down here is, remember, we've said that, look, you know, in analyzing this system, all right, even though the system is so easy, simple system, all right, unfortunately, you know, the ideas of left half plane, right half plane, root locus no longer work. So we have to look at the signals. All right, these are signals of interest to us. We then say, look, you know, this ellipsoid in tree space will be of interest to us. We then say, of course, then how this ellipsoid changes with time is of interest to us. So we take ddt of that. All right, with that, then we check for E dot, Phi dot, C dot. All right, we got these expressions. All right, and then finally we substitute them back in the V dot. Okay, now here, look at this very, very carefully. All right, look at this very, very carefully. Okay, so now what happens down here is, okay, this is the sign of the number, and this is the magnitude of the number. The sign of a number with its magnitude gives you back exactly the same number. All right, but there's a minus sign. Then what happens is that there's a gamma 1 here, there's a gamma 1 here. So the gamma 1 cancels out. All right, these two things gives you Kp. So you're getting minus Kp phi Yp E1. And if you check very, very carefully, you will see that this whole term, all right, completely cancels out this whole term. Okay, you check that carefully. Then similarly, all right, following it in exactly the same manner, I leave you to go and double check. You will see that this term cancels out exactly this second term. All right, this is quite a standard design procedure. All right, for those of you who say you know linear systems and you have signals and system, all right, if you know, you should be familiar with this design procedure. If you go and look, all right, in my own undergraduate in previous years, you know, I used to teach this too in my undergraduate, all right, in state variables, because when you come to the reduced order observer, this is exactly the procedure for the design of the reduced order observer. All right, this is run in undergraduate, okay? But this is a design procedure where, you know, you design that part of what you want to do. You design that part of what you want to do such that finally when it comes out, all right, it annihilates the required part in here. This part is you can see this was designed by us. And then when it finally comes out, it annihilates this part, leaving us with this term, all right, which is sign definite and gives us a lot of information. So yielding therefore, all right, now finally yielding therefore, okay, V dot actually just equals to AM E1 of T squared. All right, and remember by choice, all right, your reference model is a stable reference model, so AM is a negative number. So clearly then V dot is a quantity which is always less than or equals to 0. We're almost there, but not there yet. Okay, not there yet, because you have to look at these things very, very carefully. Okay, so what that tells me now, all right, what that tells me now is, okay, what that tells me now is I was interested in these signals. All right, I was interested in these signals. Okay, and then I said, let me look at an ellipsoid function of these signals. And I said, I'm interested, therefore, in how this ellipsoid is behaving with respect to time. Okay, now think very carefully, think very carefully. All right. when you started off this adaptive controller, which is exactly going back to the diagram. All right. So let's say, at the beginning of the class, I already programmed the adaptive controller, and then I got it to start. So remember, at the beginning of class, when I started this adaptive controller, E1, when I started it, E1 has some value. Okay, this was the E1 value at the start of today's class. All right. Then, since I started the adaptive controller right at the beginning of class, I had put some number down here, The correct number is supposed to be theta star, correct number is supposed to be k star, but I put some number. I can put any number, put some number. Then at the beginning, I do have my theta at the beginning of class minus theta star, and that's some number. So that's theta, that's phi, all right, the parameter error, theta t minus theta star, phi at the beginning of class. Then here, this is k minus k star c at the beginning of class, E1 at the beginning of class. Right, all these are at the beginning of class. Okay, so right at the beginning of class, when I started this adaptive controller, all right, this had some number, E1 at times 0. This had some number, phi at times 0, c at times 0. I started this at the beginning of class. All right, all these at some number. So I can certainly conceptually write down the value of this ellipsoid at the beginning of class. All right, because all these were numbers, E1 at times 0, phi at times 0, c at times 0. Okay, so conceptually this had a number. Then I was checking how it was evolving with respect to time. And up to now, in this first part now, based on my design of the adaptive controller, I've just shown you that how it evolves in time is that this ellipsoid can never grow. This ellipsoid can never grow. Okay, so I started it at some time, this ellipsoid is some size. And I've just finished guaranteeing you that by my design of the adaptive law, this ellipsoid can never grow. This ellipsoid can never grow. Okay, this now allows me to make the first conclusion. That I have the ellipsoid, all right, and the ellipsoid is such that it never grows. Then the first conclusion is that, okay, straight away I can say that in this arrangement down here of my adaptive controller, that, okay, what is happening is that these signals, all right, that they, therefore, all right, cannot blow up. They must remain bounded for all time because okay, E squared plus phi squared plus c squared basically multiplied by some numbers form the ellipsoid. The ellipsoid cannot grow because to begin with, when I started, it already was a finite ellipsoid and it cannot grow. So if it cannot grow, no matter what, the E is bounded, the phi is bounded, the c is bounded. It didn't say that the E cannot become bigger. The E can become bigger because within the ellipsoid, the E can become bigger, or the other two adjust itself, or the phi can become bigger. But never mind. No matter what, it is still all bounded in this ellipsoid, all right, and it cannot grow. And this is very important because this is no longer your undergraduate signals and systems, all right, because now in this arrangement down here, all right, the moment you put in these so-called adaptive law, the moment you put in all this so-called adaptive law, okay, your linear systems no longer hold. Okay, you check very, very carefully. You check very, very carefully. All right, E1 is YP minus YM. So there's YP in here. YP times YP is YP squared. So already you see that this part of the thing is a non-linear differential equation already, right? And the moment you have this kind of thing inside your system, all right, for those of you who are really familiar with signals and systems, really familiar, not just the simple one, you know that, all right, one of the first things that you need to do is in a system where there are non-linear dynamical equation, even before you talk about anything, you need to show me that all the signals are well behaved. All right, because in nonlinear systems, okay, linear systems, you know, even if it's an unstable system, the signals, okay, can become large. But linear systems, when they become large, at most they can only become large exponentially. They grow to infinity exponentially. But nonlinear systems, I can construct for you a first-order nonlinear system, a simple first-order nonlinear system, where, you know, I can show you that within any specified, any period you want me, okay, you say that you want it to be within 1 second. I can construct for you a nonlinear system that in 1 second has shot away to infinity. It's not exponential. You know, it is what is called finite escape. Okay, so because nonlinear systems has that danger of finite escape, when you want to do adaptive systems like this properly, this is one of the first things you need to guarantee. That, you know, no matter how fancy you're designing your signals, you better tell me that, first of all your signals are, at least are guaranteed to be still there. So now I've guaranteed you that these signals are all there. As I said, I started the adaptive control in the beginning of the class. All right, up to now, these signals are all bounded still. They're all bounded still, okay? And they're still there. They haven't, you know, taken finite escape, you know, as some nonlinear systems can, and ran away to infinity. Okay, so that's the rigorous thing that we're doing. Okay, then even then we cannot stop. All right, the next thing we will do is, okay. You also told me this was the exact expression for V dot, and this was a negative number. Okay, just to make it easier for me to see, I replace this negative number with minus alpha, where alpha is a positive number, so easier to see. So now I rewrite it. All right, I rewrite it by putting alpha. Then I integrate both sides. Okay, I integrate both sides. All right, if I integrate both sides, all right, you will see that, all right, the left-hand side, all right, being a definite integral, integrates to v at time t minus v at time 0. Time 0 was the time at the beginning of the class when I started the adaptive controller. All right, so that integrates to that. The left-hand side, I just leave it alone. Okay, then remember what is v at time 0, right? V was that ellipsoid. Okay, V was this ellipsoid. V at time 0 was the value of this ellipsoid. All right, time 0, which was the value of this ellipsoid when I started the class. So it is some number. It may be a big number, it may be, but never mind, no matter what, how big or whatever it is at time 0, okay, it's just a number. You calculate out E1 at some value, phi at some value. Okay, whether big or small, it's just some number. It's just some number. Okay, it's some number. Okay, v at time 0 is just some number. Okay, it may be a big number. Even if it's a big number, it's just some number. It's just some number. Okay, then I rearrange. Okay, I rearrange. Okay, I bring this on the left-hand side. Okay, alpha. Okay, then this is some number. Okay, and this is v of t, which is the ellipsoid. Remember, the ellipsoid function is always a positive definite function, right? It's always a positive definite function. So if I rearrange it like that and I throw this away, clearly now what I have left is that this integral must always be less than or equals to v at time 0. And remember what v at time 0 was? It's just a number. All right, when I started at the beginning of the class, it's just some number, just some number. It may be a big number, but it's just some number. Okay, and alpha was a positive number, all right, from the AM down there. What that then says as a second result is that, okay, now if you now rearrange everything properly and rewrite this thing, okay, I bring the 1 over alpha on this side. Okay, v at time 0 is still down there. All right, then when you look at this thing carefully, this is just some number. You know, it may be big or small. It's just some number which I call C1. All right. So that's the second important part of the observation. All right. It's the second important part of the observation. Okay. That now when I look at this, okay. So you see what I've gotten. The first thing that I've gotten is, all right, by my control systems design, all right, since I have this ellipsoid to begin with, and my control systems design was such that, my adaptive control system, such that I had V dot less than or equals to 0. So the first thing that guaranteed for me was that my signals were all around, all right? They were not like what was possible in nonlinear systems to run away in 1 second, go away to infinity. Then I got nothing to do, you know? But this one, no, they're all around. So it's the first thing I've guaranteed for you, okay? Then the next thing I've guaranteed for you is, hey, when you take this error signal, this tracking error signal, all right, in the adaptive control system that we put together, and you integrate the square of this tracking error signal. So you're integrating the square of this tracking error signal, starting from the beginning of class, so this is where I started, to anytime. And the property of my adaptive controller, the way I've designed it, is such that you take this tracking error, and integrate it, tracking error square, integrate it from the time I started to any time. And no matter how you integrate this error square and integrate it to no matter what time, this particular integral will always be less than a fixed number. These are fixed numbers. Alpha is a fixed number. V at time 0 was a fixed number. It may be big, but no matter how big, it's still a fixed number. So it's just C1. So what that says is that from the time you start to any time at all right, you let the adaptive control run, all right? And no matter how long it runs, the tracking error square accumulated in this square integral is always less than C1. What kind of signal is that? Okay, only then can we really properly talk about rigorous adaptation. What kind of signal might that be? Okay, let's carefully check what kind of signal might that be. So remember, this one has to be looked at very carefully. And this is a proper integral bounded from above by a fixed number. Okay, this is where, you know, for those of you, I think especially the PhD students, you all better go review your mathematics properly, because, okay, properly defined, all right, an integral properly defined has to be the still-just integral based on measure theory. Okay, you cannot go and anyhow, you know, go and don't understand integrals, which I'll talk about in a moment. All right. So basically, okay, proper integrals is the still-just integral that has to be defined by measure theory. And now that will tell us what these signals are all about. Because, you know, in the way that I program my adaptive controller, okay, I've guaranteed you that the tracking error will always obey this second property down here. Always obey. So from the time I start to no matter what time, all right, it will be like that. Okay, what kind of signal is like that? Okay, let's try to see what kind of signal is like that. Okay, let's say we look at some kind of a signal like this. Okay, let's say, try to explore different types of signal for the E1. All right, let's say we look at signal, okay? So let's say it grows, let's say it dies away, and then it grows again, but it grows, and dies, and continue to grow. It cannot be this kind of signal, right? It cannot be this kind of signal, because if this kind of signal continues to grow, right, at some point as it accumulates the E squared integral, it will violate the constraint, no matter what constraint, you know. If it doesn't violate it tonight, you know, next week class when we come, it will violate it. Because this has to be true for all t. You know, it has to be true for next week's class, even up to recess week, it has to be true. Okay, so it cannot be this kind of signal, because this kind of signal grows. Okay, maybe it might be this kind of signal in the beginning. Okay, in the beginning, you know, I'm sorry, it cannot go back on itself, causality, right? But afterwards, it must die away, right? Because it must die away, because, you know, to obey this kind of a relationship, all right, in the beginning, the signal can be anything, but by the time it accumulates enough E1 squared integral, it better be dying away because you better not accumulate any more integral. All right, so it's going to be that kind of signal. Except as I say, you have to be very, very careful because mathematically the integral is defined by measure theory by the Stieltjes integral. So indeed, it can be the blue kind of signal. Certainly, it can be the blue kind of signal. But, okay, there are mathematically those kind of signals where, even though it's the blue kind of signal, suddenly there's a spike. Suddenly there's a spike. Suddenly there's a spike. And at this kind of spike signals, the underlying measure is 0. All right. And with measure 0, even though it is a spike, it accumulates no integral. All right. It accumulates no integral at those spikes. So there is the danger that, look, even though we program our adaptive control, that, probably most of the time we behave like a blue and go to 0. But what happens if, even though it's 0, suddenly it spikes on a set of measure 0, spike like that? And that would not be good performance. And you will see that in some systems which are badly designed, where they have not taken this into account, you see this kind of spikes happening, right? So when Tom is talking about deep learning, okay, deep learning, you all have seen this. You all have seen this because, on sets of measure 0, this kind of spike can happen because, something like this only guarantees me up to the part, but doesn't guarantee me no spike. But in our case, we have more than that. We have more than that because after all of that, all right, in addition, okay, we also have, all right, okay, check E dot, all right, AM is just a number, E1 we have shown to be bounded, right? We've shown it to be bounded, E1 we've shown it to be bounded. We've shown E1 to be bounded. All right, E1 we've shown to be bounded, KP is just a number, Phi we've shown it to be bounded, YP from E1 is just YP minus YM. YM is your reference signal is bounded. If E1 is bounded, YP is bounded. Okay, we've also, KP is a number, Phi is bound, C is bounded, R is just your reference signal is bounded. So here, in addition to the fact that we have this square integral satisfying this upper bound, next thing that additionally that we have, all right, is that E dot itself is a bounded signal. All right, if E dot is a bounded signal, so certainly because of the square integral condition, I certainly can tell you that my signal will look like the blue one. And it will not admit the kind of spike signal because in addition, I have E dot being bounded because for this kind of spike function with 0 measure, E dot is not bounded at the spike function. All right, so I've guaranteed that separately by having E dot bounded. And together, all of this result then, so we also have, all right, with the above, E dot is bounded. All right, for all t greater than or equals to 0, or greater than or equal to the time that we started the adaptive control. Then all of the above together, all right, gives me this result that in the way that I've set up my adaptive controller, indeed, all right, my adaptive controller guarantees me the tracking of the reference model that I want. Okay, so as I said, I wanted to address this very simple example, but you see all the key ideas are coming up now. All right. Philip, bounded means it is bounded. All right. E dot less than or equals to 0 says E dot is negative. Philip, I think, as I said, that's why I want to stop here tonight. If I said too much more, you all would have even forgotten about what is boundedness and what is negative. That's why I was very clear. I will stop here. Philip. Okay, I'll stop here. Let me also stop the recording. All right. Okay, tonight I will upload the recording quite quickly too. I will also upload